right, and today we begin the final segment of this conversation about everything you ever wanted to know about the Earth and more. If we didn't cover it and it's some random fact, by the time we're done with this, you guys certainly feel free to ask me or email me, because this has been a hodgepodge all over the place. Not really random, just we're building to perspective, as I said, but just a whole bunch of ideas sewn together. So I tried to segment it up with lectures, kind of try to find a logical place to end before we start a new topic, so on and so forth. So hopefully that's helped you keep it organized. We left off talking about the fact that we finally had an atmosphere, our first atmosphere. And looking at it, if you pay any attention to planets and stuff like that, you might say, wow, that looks like an atmosphere on Venus or Neptune or something. Okay. Certainly not. Certainly not what we've come to expect for Earth. And no, it takes time. We started with this, okay, and over the eons, literally, we have modified it to what you see today. And as many will argue, we're continually modifying it by since the industrial age, right, where we started burning up things that have been stored forever, releasing more gases into the environment, sort of creating our own little outgassing event for the last couple hundred years. So everything is always changing. Well, once you have an atmosphere, especially an atmosphere that's chock full of water vapor, you are bound to have something we know called weather. We haven't talked about the water cycle in here yet, so I'm going to give you a brief little rundown, at least a part of it. You guys have had the water cycle undoubtedly somewhere in life already, but just a reminder, a refresher, if you would. So the sunlight evaporates water at the Earth's surface. What does evaporation mean? It's a change from what to what? Liquid to gas. Awesome. So the sunlight warms up liquid water, turns it into gas, this gaseous water, which we call what? What do we call water gas? Water vapor. Good. All right. That water vapor floats up into the atmosphere. Once it's up in the atmosphere, it cools back off and turns back into liquid water. What do we call the process where we go from a gas to a liquid? Not evaporation, it's the opposite of evaporation. Condensation. Condensation. All right, we're going to precipitate in a moment or two. So it condenses, the water vapor condenses into droplets of water, which eventually form these things we've come to know and love called clouds. And I think once you've got air and clouds, most folks would, I think, officially give that the stamp of being an atmosphere, right? It's just more official once you've got those clouds up there, along with your sun and whatnot. Anyhow, as you may or may not know, over time, those cloud droplets get bigger and bigger and bigger. And eventually they're no longer able to be supported in that cloud, and they start to fall out of that cloud. That cloud falls apart. That is the precipitation part. It's not a phase change, really, but it is the water droplets falling back down to Earth to accumulate somewhere or percolate into the Earth, and so on and so forth, and complete that cycle again. Now, did I leave a few things out? Of course I did. Okay. That's just a small portion of the water cycle, but it's all we really need for this conversation. Of course, clouds can also be made of ice crystals, all right, not just liquid water. Oh, and that is something I usually harp on quite a bit. A lot of folks think clouds are gas or water vapor because they look like steam, maybe. Please understand that clouds are water droplets, okay, or ice crystals. They are not water vapor. All right, so what we're doing at this point is saying that up in the atmosphere, all of this water vapor that came billowing out from the outgassing event has started to condense into water droplets, forming clouds. It's a moderately arguable point, but at this moment, we do not have any surface water yet. All right? It's tough to nail down exactly what happens. What I'm giving you is the general narrative of the order of progress, but there's folks studying this all the time. And we'll see in a couple moments the angle that the other folks are using. All right, so anyhow, with clouds, eventually it will start to rain, okay? Especially if there is more and more water vapor to keep building those clouds up bigger and bigger and bigger. And if that is an ongoing event, remember this outgassing is happening potentially for a very long time. So, talk about not being able to put a number on something. This is a great example. All right. We can't tell you how long this went on, more than likely. I'm sure somebody out there is trying. But what we can tell you is that, for the most part, the way we currently see this time period, as I said a moment ago, there was no surface water. How long did it rain? How much did it rain? Enough to make the oceans. And I know that's a lot to swallow, pun not intended, but it's a lot of water. All right? But we're talking about worldwide volcation's not a word either. Worldwide eruptions, let's just go that route, for potentially a very, very long time. Rain acted exactly the same way back then as it does now. We have no reason to think otherwise. Some of you may remember from earth science something called the principle of uniformitarianism. Okay, we have no reason whatsoever to think that gravity worked differently back then or rain worked differently. It just principles that apply now should have applied in the past as long as you're looking at the same parameters. So just like now, back then, rain drained to the lowest spots. You might recall that we talked about the two different kinds of crusts, the oceanic crust and the continental crust. And I mentioned real quickly in passing that one was more dense than the other. All right? It seemed insignificant at the time, and it really numerically doesn't look like a huge difference. But because of that, the oceanic plates were already sitting lower than the continental plates. Okay? Enough so that when water fell on the continents, it eventually drained to the oceans. All of that water pushed those oceanic plates down a little farther, made those low spots even lower, which in turn buoyed up the continents a little bit. Anyhow, it rained, and it rained, and it rained, and it rained. Okay? What I'm teaching you here is that outgassing is the primary source of the Earth's water. Okay? And you will see that on the test. It's going to ask you flat out, as discussed in class, what is the primary source of the Earth's water? And if you want to get it right, you'll say outgassing. Now, I mentioned there was something else. We talked about all the craters. Remember all the craters? Well, not everything that smashes into something is a rocky or metallic asteroid. Some of them are also comets. And so you can look up at the moon and designate a certain percent, let's just say, of those pockmarks to cometic impacts as opposed to asteroidal impacts, meteoritic impacts. Comets are composed, they usually call them what? Dusty snowballs, dirty snowballs. Okay, we've known for a while, more or less, what they consist of. They're pretty good at shining up their telescopes and looking at different colors and guessing the chemicals that are in things. Again, it's a little more complicated than that, but that's, nutshell version of it. And as it turns out, the water that's in comets is a slightly different isotope. Remember isotopes? All right. This is a slightly different version of something you already know exists. So it's a different kind of water. It is certainly present in the oceans. We cannot argue that comets did not hit the Earth and melt, for lack of a better word, or probably vaporize and then fall as rain themselves, right? You can argue who came first. And I think there's a great chance that we did get hit by a couple comets before outgassing got started. You never know. But there's zero evidence that it did. There's no impacts from back then that we found at any rate. But there's definitely comet water there. So a secondary source of the Earth's water is definitely comets, okay? Like I said, they could look at, take a sample of the ocean water, a couple dozen samples, and, you'll find some cometic water in there, but mostly it's what we'll just call Earth water. Now, if somebody could come along and prove that comet water decays into Earth water, breaks down into Earth water, then that's a whole nother argument to have. Yeah. Huh? Oh, well, for one thing, we finally landed on one not too long ago, and we got a sample. The same way we just bumped a missile into a satellite into an asteroid the other day. All right, just damn good luck. And a lot of calculus. But we landed on one. Oh, good God, it's been 10, 15 years ago? Nah, they're supposed to be ice. They're supposed to be, like I said, very dirty. Imagine, a dust bunny that's been outside all winter. It's got everything in there, but including, frozen. That's the tail, supposedly, is the water vapor coming off of it. So, as it melts through there and various amounts of dirt and grime trailing along too. It's really sort of like solar system trash bin stuff. But as I understand it, at any rate, all of this is as I understand it. And I try to keep up on new developments. But yeah, we did land, and it's something to do, it might be Eros. And I think we landed on it right around Valentine's Day as well. There was some big, it was all in the news, but you guys were probably like 4, so. We landed on a giant ice ball, yes. Yeah, no, it was maybe a little bigger than a school bus. I don't think it was huge. It might have been a football stadium size. Hold on. Folks at home, I'm going to pause you for a minute. All right, you folks at home, we did a quick internet search, and I did not find anything that directly verified what I said about landing on a comet. I'm still pretty damn sure we did that, but we certainly have a couple instances showing up of going through the tail or going into the dust clouds surrounding it and grabbing samples. So there is that, but remains to be verified. So again, primary source of the Earth's water is what, you guys? Outgassing. Secondary source is comets. All right. Okay, so I used to, back when I gave like what are pedagogically considered to be good tests, where you have a variety of questions that ask things in different ways and so on and so forth. I had what I thought was a wonderful exercise where you would put up a chronology. And I expected that chronology more or less to go kind of how I presented it in class. And oh my God, they did so bad on it. Horrible. So I tried reworking it. And we got it slightly better. But if you got one thing out of step, you know how those things go. Everything else is wrong afterwards. And the more I started thinking about it, because it had originally been an essay question. Okay? And I turned that essay question into a chronology, again, to try to get stuff back faster. Well, through that process, I realized that this is all kind of nebulous. There's a whole bunch of stuff happening more or less at the same time for a very long period of time. And yes, you do have to have some things before other things, but I think I was asking a bit much for you guys to, after one lecture of discussion, to process how important the order was. So I've kind of shied away from that now, and what it's turned into, unfortunately, are seemingly random vocabulary words. Now, photochemical dissociation, for example. Okay? But it's all part of a moment in the Earth's history. Okay? So, for example, time-wise, we couldn't have photochemical dissociation until after we had outgassing. Okay? We need the outgassing to put all this stuff up there. It couldn't have started raining until after outgassing. Now, did photochemical dissociation start before it rained? Sure, quite possibly. Okay, again, the exact order isn't important, but the relative happenings of things are. And don't worry, I don't have any chronologies, but just trying to illustrate that these are still sort of all connected. So photochemical dissociation is a pretty standard process. It's still going on today. It's going on right now, more than likely. And what happens is that water vapor in the presence of sunlight is broken apart. The molecule is split up. Photo means light. Okay? Think about photograph. Graph means picture. Photo means light. So they're light pictures. All right? Photon, you've heard of that before. So photo means light. Chemical, well, chemical just means chemical. Dissociate. Break apart, split apart. You may not use the word dissociate, but your old boyfriend or girlfriend or a friend you no longer hang out with, you are disassociated with them. Okay? So, light chemical break apart. Literally the word means the definition. All you have to remember is what chemical we're talking about here. And that is indeed water vapor. And this is important. Again, the definition is one thing, but the relevance is something else. This allowed us to make ozone. All right? This allowed us to make ozone, which is, as you know already, rather important. Ozone is O3. We like to breathe O2. Ozone doesn't taste so good. If you've ever been in a big city and you had a taste of that smog, they call it, okay? That's a lot of ozone. There's other stuff in there too, but ozone has kind of a bitey in the back of your throat taste, okay? People, when they first see this, say, oh, cool, this is where we get our breathable oxygen. Doesn't turn out that way. Oxygens love to stick together, and for whatever reason, well, there are definitely reasons, but they went straight to O3 instead of O2. So we're building our ozone layer now through a totally natural process. And presumably it was in the stratosphere then, just like it is now. Something about, perhaps the altitude that helps these chemical processes go. Something about this, that, or the other thing. But the ozone more or less has positioned itself to be a stratospheric level occurrence. So photochemical dissociation splits up water molecules, and that's important because that allowed us to make ozone. Okay? So again, in the ordering of things, that chronology, you can't have the ozone layer showing up before you talk about photochemical dissociation. That allowed it to build.